Section 6.4, Matrix Arithmetic. Part 1, Operations with Matrices. Two matrices are said to be equal if they are the same size and the corresponding entries are equal. So if I want to use the equality of the following matrices to solve for x and y, I'm saying that the matrix on the left equals the matrix on the right. That means all of the corresponding entries need to be the same. First row, first column, those need to be the same. First row, second column, those entries need to be the same, etc. So to solve for x and y, the one I just circled, I had 4 has to be equal to 2y. Divide both sides by 2, and I get y equals 2. So because these two matrices are equal, I know that y has to be equal to 2. To solve for x, second row, first column is x minus 3 in one matrix and 5 in another matrix. So they have to be equal. Add 3 to both sides, and I get x equals 8. So x is 8 and y is 2, because these two matrices are equal. Let's talk about matrix addition. Given two matrices of the same size, the matrix obtained by adding the corresponding entries of the two matrices is called the sum. So what that means, if I want to add two matrices, here's A and B, I want to add the two matrices. Notice they are the same size. They have to be the same size in order to add. So this one is 2 rows, 3 columns. This one is 2 rows, 3 columns. If they're not the same size, we cannot add the two matrices. So to add these two matrices, we're just going to add the corresponding entries. So first row, first column, 2 plus 1 is 3. First row, second column, -2 plus -5 is -7. First row, third column, 4 plus 6 is 10. And then I'll do the same with the second row. 0 plus 4 is 4. -3 plus -2 is -5. And -4 plus -3 is -7. Now I've added these two matrices. I found A plus B. Any matrix whose entries are all zeros, we call the zero matrix. The zero matrix is the additive identity for matrices. That means we can add the zero matrix and it didn't change anything. That's the same for real numbers, right? If I take, say, any number, say 9, and I add 0, I still have 9. It works the same way for matrices. If we add the zero matrix, we haven't changed anything. So, for example, the 2 by 3 zero matrix is this matrix right here, where all of the entries are 0. So for any 2 by 3 matrix, A plus 0 has to equal A, has to equal 0 plus A. So let's show that A plus 0 equals A for this matrix here. That means I want to show that if I take this matrix that's given, matrix A, and I add the zero matrix of the same size, then I get A. So let's add these and see what I get. If I add the corresponding rows and columns, add all the corresponding entries, I'm just adding 0 to all of these numbers in the first matrix. So nothing changed, and I end up with A. The additive inverse of a matrix we can call -A, and it is the same size as A, but all of the corresponding entries are the opposite. So if I have two matrices and they are additive inverses, then if one entry, say row 1, column 1, is a 3 in one matrix, then in the other matrix, it would be a -3, just the opposite of each other. So let's find the additive inverse of this one. So the additive inverse, or -A, we're going to change the sign of all the entries. So I have -2, 2, -4, 0, 3, 4. I just changed the sign of all the entries, and that's the additive inverse. Now what happens if I add matrix and its additive inverse? If I add these together, I should get the zero matrix. And that is true in this case. 2 plus -2 is 0. -2 plus 2 is 0, etc. It will work for all the entries because these are additive inverses. Matrix subtraction is just adding the opposite. Same with real number subtraction. If I take 9 minus 5, that's the same as 9 plus a -5. Works the same way with matrices. So if I want to subtract or find the difference of these two matrices, A minus B, that will equal A plus the opposite of B. So I'll change all the signs on B. So I multiplied all the entries in B by -1, if you want to think about it that way. Now I'm going to add these two together. So I've changed this to a plus by adding the negative. If I add these together, the first row, 2 plus -1 is 1, -2 plus 5 is 3. Second row, 4 plus -6 is -2, 0 plus -4 is -4, and third row, -3 plus 2 is -1, and -4 plus 3 is -1. So I have subtracted these two matrices. I found the difference. Scalar multiplication is the next definition. We define the product of a real number k and a matrix A, denoted as Ka, to be the matrix obtained by multiplying each entry of A by k. So k is what we call the scalar. It's just going to be a real number. So if I have something like this, so my matrix A is this matrix shown here, I want to find 2A. So 2A would mean that we're going to multiply all the entries by 2. So the first row, 2 times 2 is 4, 2 times -2 is -4, and 2 times 4 is 8. Second row, 2 times 0 is 0, 2 times -3 is -6, and 2 times -4 is -8. So we call this scalar multiplication. 2 is the scalar because we scaled up by a factor of 2. All of the numbers got multiplied by 2.